Lockheed Martin is building ships. Why would an aerospace titan learn to sail? The secret is their world-class expertise in advanced composite materials.
Lockheed Martin, long celebrated as the undisputed king of aerospace with masterpieces like the F-22 Raptor and F-35 Lightning II, has been making increasingly bold strides into the maritime domain. This move is far from a random diversification. Rather, it represents a highly logical strategic evolution driven by the converging demands of modern warfare. The company typically does not build traditional massive steel shipyards itself, instead positioning itself as the primary contractor and systems integrator for naval projects. Through partnerships with specialized shipbuilders like Fincantieri Marinette, Lockheed Martin has already left its mark on programs such as the Freedom-class Littoral Combat Ship, LCS, and various unmanned surface vessels, USV. The fundamental question remains: why would a giant of the sky harbor such grand ambitions on the water? The answer lies in the convergence of cross-domain technologies, with their ultimate trump card being advanced composite materials. More pragmatically, they are not trying to compete with traditional shipyards on tonnage, but rather to extend the life cycle of their expensive aerospace manufacturing facilities by finding a second high-volume market for their core expertise. Lockheed Martin's maritime strategy is built upon the transfer of its unparalleled expertise in composite materials, specifically carbon fiber reinforced polymer, which was perfected for aircraft like the F-35. These materials offer a revolutionary dual-purpose function when applied to a marine environment. And the first advantage is their exceptional resistance to galvanic corrosion caused by salt water. While it is more accurate to say they are highly resistant rather than completely immune, since resin matrices can still absorb moisture and face delamination risks if not properly coated, the reduction in long-term maintenance is still drastic compared to traditional steel alloys. The second major advantage is extreme weight reduction, a principle held sacred in aerospace engineering. Replacing steel superstructures, masts, and deck houses with composites can slash weight significantly. Industry experts often cite a best-case potential of up to 40% savings for specific structural parts, which directly translates into a more agile vessel with superior fuel efficiency and a lower center of gravity, ensuring exceptional stability even in rough seas. Perhaps the most transformative capability unlocked by composites is the enhancement of naval stealth, though the reality is more nuanced than a simple material property. The F-35's low observability is a systemic achievement, relying on precise geometric shaping, rigorous edge alignment, and specialized radar-absorbing materials, RAM, applied over carbon fiber substrates rather than the composite alone absorbing radar waves. In the maritime domain, Lockheed applies this same systems-level thinking to design integrated masts and structures that allow RAM to be embedded into the composite skin, which can measurably reduce a warship's radar cross-section, RCS. To manufacture these large-scale structures, the company demonstrated a low-cost vacuum-assisted resin transfer molding, VARTM, for the Trident II D5 missile structure, achieving a 75% cost reduction through part consolidation. However, it is important to note that the U.S. Navy had already utilized similar VARTM techniques for composite deck houses since the early 2000s, meaning Lockheed is a highly skilled practitioner rather than the originator of the broader out-of-autoclave trend. Crucially, Lockheed maintains extensive composite fabrication facilities in Marietta, Fort Worth, and Palmdale, originally built for aerospace programs. While there is no public confirmation of these specific sites currently producing full-scale maritime hulls, their technical capability suggests they could potentially be leveraged for large maritime prototypes without requiring entirely new factory infrastructure. Lockheed Martin is not merely applying old technologies to new platforms. It is actively investing in the future of maritime warfare through autonomous systems and next-generation manufacturing. The company made a significant $50 million strategic investment in Saildrone on October 29, 2025, aiming to rapidly equip these long-endurance USVs with all-domain defense technology, including the direct integration of the JAGM quad launcher. This move highlights their focus on creating lightweight, mass-producible platforms, where composite structures are essential for carrying heavy payloads while maintaining speed and range. Simultaneously, through its venture arm, Lockheed Martin Ventures invested in Perseus Materials, a startup developing what is described as the world's fastest large-scale manufacturing system for composite parts. Lockheed notes that this process could drastically reduce costs and eliminate the need for expensive tooling, which directly addresses the challenge of building large vessel components without custom molds. These investments clearly indicate that Lockheed's goal is to dominate the production of smart, attritable, autonomous fleets rather than competing with traditional shipyards on the number of steel hulls produced. Ultimately, the deeper rationale behind Lockheed's maritime push, as analysts infer rather than the company explicitly states, aligns with a classic aerospace strategy, leveraging sunk costs in advanced composite production to secure a parallel high-volume market. The company already masters a supply chain for CFRP and prepreg in its existing facilities, and as fighter programs mature, finding adjacent applications makes sound business sense. The maritime domain fits perfectly because the engineering demands, weight reduction, extreme environmental resistance, and signature management are remarkably similar. This strategy extends below the surface with proposed concepts like the Lamprey MMAUV, a stealthy autonomous underwater vehicle designed for disruptive operations, though it remains primarily in the concept and demonstration phase rather than full operational deployment. For such a vehicle, a filament-wound carbon fiber hull offers a superior strength-to-weight ratio compared to steel, though titanium remains a competitor with its own trade-offs regarding fire resistance and fatigue. Crucially, composite hulls are inherently non-magnetic, a property that can naturally help reduce detectability by magnetic anomaly detector (MAD) sensors, although the overall signature ultimately depends on other onboard components like batteries and motors. Lockheed applies its OOA curing expertise to form these pressure cylinders and integrates conformal sonar arrays directly into the skin, following the same logic as their established low-cost conformal arrays for submarines. Thus, the final narrative is one of technological convergence, one aerospace-grade resin and advanced manufacturing process applied across two domains, ensuring Lockheed remains an architect of the future fleet without necessarily replacing traditional shipbuilders.